Hello everyone, I'm Pengfei Li from Alibaba Group. I'm very happy to share this work with you. The work is entitled Daily Distribution-Driven Learning Index. It's a joint work with Hua, Rong, Bolin, Long, and Gang. Okay, let's begin with the motivation. Recently, the idea of a learning index is proposed. That is, B-tree can be replaced with machine learning models indexing one-dimensional data. As you know, a traditional index such as B-tree can be regarded as a mapping from a K to a position inside a sorted array. Thus, in machine learning terminology, the index is simply a regression model. By replacing it with a learning index, the query performance can be improved. However, existing state-of-the-art learning indexes still have some drawbacks. For example, the number of Alex fans is relatively static. Also, the models in Alex leaf nodes don't guarantee accurate predictions. Thus, extra local search is needed. The design of IIPP ignores the data distribution and often results in long traversal paths. In addition, it consumes much memory cost. To address these issues, we propose Daily. It is a distribution-driven learning index with better search performance than existing indexes. Also, it doesn't need local search and supports data update. First, let me show you some basic settings. In this paper, the keys are assumed to be one-dimensional numbers. The key value pairs and indices are saved in the main memory. Our proposed data is an index tree that is composed of two types of nodes, internal nodes and leaf nodes. To build Daily, we propose a two-phase bulk loading approach, which requires an initial dataset. In this approach, another distribution-driven bottom-up tree will be built first. Its node layout can consider the key distribution. Furthermore, as we mentioned, Daily supports to process insertions and deletions. Okay, let's start with introducing Daily's structure. This figure shows it. The internal nodes are represented by rectangles, while the leaf nodes are represented by circles. Each node in Daily contains a linear regression model LR and an array for indexing purpose. Such models and arrays serve different purposes in the internal node and the leaf node. The search process in Daily can be roughly described by two parts. The first part finds the leaf node whose range covers the given key. This part covers step 1 and step 2. After that, the second part will conduct the search in the leaf nodes, as shown in step 3 and step 4. Okay, let's see how the internal nodes and the leaf nodes looks like. An internal node NT stores a linear regression model LR and an array C of pointers to NT's child nodes. Note that each element in C is a simple pointer without any keys. Also, NT's child nodes equally divide each range. Thus, an internal node doesn't need to store an additional ordered set of elements to describe the child node's ranges, because they are clearly described by the linear regression model. Given a kx, we can easily know which child node covers x with a few simple calculations. When a search goes down in the tree, NT uses LR to compute the location in array C of the pointer to the next child node to visit. A leaf node ND stores an entry array V and a linear regression model LR. Each entry is a pair, a pointer to another leaf node, or a null flag, indicating if the corresponding slot of V is empty. The learned model LR maps the key to a position in V. It is the solver to an MSE problem, whose input is the keys covered by the ND's range, and the ground truth is the corresponding indices. V also covers pointers or null flags due to the local optimization strategy. This strategy uses machine learning models to directly determine key storage positions instead of approximating them and forcibly place pairs at the return position. If the predicted positions of multiple pairs are the same, that is, they conflict, a new leaf node will be created to deal with them. The details of the local optimization will be introduced later. Recall that the linear regression model in an internal node NT has perfect accuracy because each children equally divide each range. The design gives rise to a unique critical problem in constructing delay, deciding the suitable fan-out for NT. Here, the fan-out of a node refers to the number of each child nodes. We propose a two-phase bulk loading algorithm to assign a suitable fan-out to each node. First, we create a build tree, short for bottom tree, starting from leaf nodes and growing the tree upwards. Second, we reuse the build tree's node layout to build a delay and improve the latter's linear regression models such that they can also obtain perfect prediction accuracy. The built delay is able to find the leaf node covering a search key with only a few calculations of linear functions. Also, the local search time cost in the leaf nodes is small as the delay has a leaf node layout similar to the build tree. Their delay is built in a novel paradigm, that is, we first design a mirror model that finds leaf nodes efficiently, and then create a similar model that further optimizes local search in a leaf node. Before showing how to generate the build tree, I want to briefly introduce its structure. It is a balanced tree and also composed of internal nodes and leaf nodes. A build internal node NT is structurally the same as that in delay, except that the NT stores an additional array B to record the ranges of all its child nodes. Note that the child nodes now may not equally divide the NT's range. All build leaf nodes are at the same height level, and they are reused as the basis of the leaf nodes in delay. Key search in a build tree is different from delay. Finding the child node covering Kx in a build internal node NT involves two steps. The first step computes a predicted child node position in the child node array using the linear model, and the second step searches from the predicted position to find the correct index. Build tree is built in the bottom-up manner. The core algorithm of each construction is the gradient merging. This algorithm will first take all the keys as input and split them into a suitable number of pieces, with each piece referred to a build leaf node. That is, this leaf node will cover all keys in the corresponding piece. Then, all build internal nodes will be created in a bottom-up way, also with this algorithm, until an appropriate root node is found. Note that the boundary points of ranges of the nodes at the last level will be used as the input to generate the nodes at the current level. At each height edge, we independently decide if the nodes at the current height should be the children of the root node or not. The gradient merging algorithm automatically splits input keys into a suitable number of pieces as long as a cost function is given. The suitable number k is decided as follows. Initially, k is set to be half of n. In other words, the input keys are partitioned into half of n pieces. At each iteration, we merge two continuous pieces that results in the most total loss decrease until the loss does not decrease. Then k pieces are generated, with each piece referred to a build node. Our used cost function takes the list of the boundary points of the pieces as input. It estimates the average search cost until height h in the generated delay. If the build node layout at height h is determined by current pieces, thus the estimated search cost of the generated delay instead of the build tree is minimized. Due to time limits, I omitted each explanation here. Please refer to our paper for more details. It's time to show how to convert a build tree into a delay. First, the height of delay and the build tree will be the same. At any height, delay and the build tree have the same number of nodes, but the node layout may be different. Based on the build tree, we grow delay top-down. The range of delay's root node is set to the counterpart in the build tree. The fan-out of a delay internal node ND at height h equals the number of BO nodes at height h-1 whose range is covered by ND's range. For example, in this figure, the height of the delay node ND is 2, and its range is from 0 to 60. This range covers 4 BO nodes at the height 1. Thus, the file out of ND is set to 4. Note that we didn't process the keys in Daily's leaf nodes now. Thus, we need the last step to generate the daily. Our last step is to carry out the local optimization operation to each of the leaf nodes. A leaf node's linear regression model approximates the relation between keys and their position in the entry array. However, no model can always make perfect predictions. We find that the local search in the leaf nodes often forms a bottleneck. To address these issues, we propose a local optimization for Daily's leaf nodes. It helps the linear models make perfect and accurate predictions and avoid element shifting in insertions. The local optimization is simple. If the linear regression model predicts a same position T for multiple pairs, we create a new leaf node to cover them. After that, the pointer to the newly created node is assigned to the position T in the entry array V. It is easy to insert a pair using Daily. First, we find the lowest leaf node that covers the pair's key. Then we use the linear regression model in the leaf node to calculate a position in its entry array. If the corresponding slot is empty, we simply put the pair at this slot. Otherwise, there is another pair in this slot and a conflict happens. In this case, we need to create a new leaf node covering the two pairs and put the pointer to this node at the slot. Also, Daily flexibly redistributes data covered by a leaf node in a balanced way. When insertions generate too many nodes and degrades the query performance. The procedure of deleting a key in Daily is similar with that of the insertion. If a leaf node covers no key after the deletion operation, it will be removed. More details can be found in our paper. We conduct extensive performance evaluation using real and synthetic data. Traditional indexes like B+tree, MathTree, and existing learning indexes like IMI, ALEX, IS, PGM, and LIPP are compared with Daily. We compare them in terms of different evaluation metrics like lookup time, throughput, average cache misses. Also, we conduct experiments to compare Daily and the alternatives on different types of workloads. The read-only workload contains point queries only. The read-heavy workload contains 1/3 of insertions and 2/3 of point queries. The write-heavy workload contains 2/3 insertions and 1/3 of point queries. The write-only workload contains insertions only. All of the experimental results demonstrate that the Daily outperforms traditional indexes like B+tree and existing learning indexes in terms of multiple evaluation metrics. In this work, we designed for in-memory 1D case a distribution-driven learning index Daily. The search inside a node is performed by an efficient linear model. An internal node's key range is equally divided by all children, endowing internal nodes with perfect accuracy for finding the leaf node covering a key. We optimize Daily's node layout by a two-phase bulk loading approach. Also, we design algorithm for Daily for data updates. For future research, it is relevant to adapt Daily to disk-resident data. Moreover, it is interesting to consider concurrent data updates. Also, we will investigate if other types of models will result in better performance than the linear regression models. Thanks for your watching.